Hello guys, and welcome to a new chapter on integration. So today what we're going to be discussing is limits, indefinite integrals and definite integrals. So this episode is essentially, if you're completely new to integration, I highly recommend this video. If not, I recommend the next video that I'll be releasing. So this video is about laying the foundations down about integration, how to do it, and then we'll solve exam type problems later on. So, in a summary, what is integration? So integration is essentially finding the area underneath a curve. That's essentially it. So, let's begin. We're going to begin with limits. So, let's consider a XY graph. Okay? So, what we want to do is let's draw a graph of y equals x squared. That's just what we're going to draw at the moment. So, from this, we can say that, okay, so how will we find the area underneath this graph? Surely that's not possible, because from every formula that you've learned at GCSE, you generally have no idea, because there isn't a general formula. For example, like an area of a triangle, area of a pyramid, or a surface area of a pyramid, surface area of a sphere, for example. However, there is a general technique that you can use. And we're going to go straight from these limits into indefinite integrals, and then we'll discuss about limits and then definite integrals. So it's just laying down the foundations for you. In general, how the hell are we going to find the area underneath the curve of y equals x squared? Well, let me show you an example. What we're going to draw is we're going to draw rectangles. Okay. I'm just going to draw 5 rectangles so it's easier. So these rectangles span infinitely that way and infinitely the other way, for example. This is just, x. So pretty much with this graph is, that's our domain, for example. Okay, so how the hell are we going to do this? Because surely you have no idea, I have no idea, so let's do it. Each width of the triangle, each width of the rectangle is delta x. That's each width, so every rectangle, I was about to say triangle again, has a width of delta x. And each rectangle has a variable height of x squared. So the small rectangle has a height of x squared, and so does the tall one. Now we can label this as a series, so we can sum the area of each rectangle to get an approximate answer to what is the area underneath x squared. So what we can say is that the sum of x squared, the area is the sum of x squared times, that the little dot means it's a scalar, but it can mean times as well. Makes things more simplified. Times delta x. So this is the sum of all the areas of all the rectangles, added up. Now, what integration is, integration tells us that as the strips of rectangles get smaller and smaller, the area becomes the same, essentially. But I'll show you what happens So, the limit as delta x equals 0, summating x squared times delta x. And as these rectangles, as these rectangle widths are getting infinitesimally smaller and smaller, it will become an integral. So, as the width tends to 0, this will turn into the integral, which is in linguistics, I think it's called a schwa, I'm pretty sure, of x squared with respect to dx. And that's it. And that's literally it. There was a question on the 2019 Maths Paper 2 on Edexcel, which had this sort of question. It was like, calculate the limit of when delta x tends to 0 of this, essentially, with limits, because it's a definite integral. So, and many people got stumped on it and they had no idea what to do. However, this is what to do. It's literally this, as the limit of each width of the rectangles gets towards 0, it turns into a perfect curve. That's why we can find the area under a curve. Now, you're probably thinking, well, I've got up to this point, so what do I do with it? Because obviously you don't know how to integrate, so I will show you. Now, let's take x to the power of n, where n is a constant. So when n is a constant, that means it can be 1, 2, 3, 4, 5, 6, 7, 3 over 2, 5 over 2. I don't know. It can go up to, not infinity, but it can go up to pretty large numbers. When you integrate x to the power of n with respect to dx, the general formula to use is x to the power of n plus 1 divided by n plus 1, where n is, of course, a constant. So you're probably thinking, okay, let's do this. Let's use this general technique. I will square that for you. Let's use this general technique onto this term. So, when we integrate x squared with respect to dx, we will get x to the power of 2 plus 1, all divided by 2 plus 1. So pretty much our n in this case is 2, and this is what's happening. So then we will get an answer of x cubed over 3 plus c, where c is an arbitrary constant, because this is an indefinite integral, so we don't know what the boundary conditions is. This is the general solution, not a particular solution. The difference is a general solution is, it's just a general solution. I can't really know how to explain it, but a particular solution, you are given boundary conditions. For example, when y equals 0, when x equals 1, for example, and then you would use to find out c. And then that is a particular point on the curve. So that's what it is. And that is literally indefinite integrals as a whole, pretty much. So, I'll cover another one where we deal with a constant in front of a integral. Okay, let's calculate the limit of when delta x tends to 0. So each rectangle, the width becomes 0, so it becomes a perfect curve of x cubed times delta x. Let's calculate that. So all this becomes is an integral of x cubed with respect to x. What do we do from there? Oh, sorry. let's say, sorry, 2x cubed. Let's say 2x cubed. Okay? In this limit, we can do exactly the same as we can do in the integral, which we will do shortly. We can factor out any constants that we need to, just to help us simplify. So then this integral becomes 2 factored on the outside, x cubed with respect to dx. This makes it a whole lot easier, mainly because we don't have to deal with this 2 in this general formula. The constants are independent from each general formula. That's a good thing. So, what is this? So 2 times x to the power of 4, so 3 plus 1 equals 4, all divided by 3 plus 1, which is 4. So therefore, we can say that this integral, or plus c, is equal to a half x to the power of 4 plus c. And that's it. That is literally indefinite integrals within about 11 minutes, give or take. So I'm going to talk about definite integrals now. Oh, sorry. One more thing I have to mention is that if you have an integral in the form of square root of x or integral of cube root of x dx, you always have to rewrite these forms into this will be the integral of x to the power of a third dx, and this would be the integral of x to the power of half dx. So make sure you know your rules of indices, because if you don't, you're screwed. And this is particularly important for if you're struggling to do integration and you need a general technique on how to integrate, and you need to write, if you really want to memorize these, then by all means, but it makes it a whole lot easier by rewriting it in the form that we need to. So I'll put on some questions that you can do. So those are 5 simple integrals that you can find, and then pause the video, go and do these, and then you'll be fine, and then you'll be sorted. Now what we're going to do is that we're going to discuss definite integrals. So definite integrals we are going to discuss. Now, a definite integral is an integral with limits involved. So those limits are boundaries that you cannot go past or can't go back, if that makes sense. So, for example, let's consider y is equal to root x, for example. How are we going to find that? So, let's say that this limit is 2 and that this limit is 4, okay? And then this is, and that is our region. Regions will be always sometimes be labeled R, if not A for area, simple like that. But mainly they note it as a region. So how are we going to find this? So we do our rule again, where we add up and summate all of our strips of rectangles of width delta x and our height root x. So what we do is the region involved is equal to the sum between two and 4 of root x times delta x. So what this is saying is that the bottom bit is our start term. So we start from our limit of 2 and then we end at 4. So for example, the width is our delta x, and the square root of x subscript I, the I is 2, 3, 4, 3 over 2, no, sorry, not 3 over 2, 5 over 2, 7 over 2, whatever it is. This is just to make sure that we know how many strips we're considering. So, again, as I've already mentioned, as the width gets infinitesimally smaller, the region becomes more accurately defined. So we can say that the limit as delta x tends to 0 between the sum of 2 and 4, sorry, the limits of 2 and 4 of x root x subscript I times delta x. So we can literally label this as an integral. So we can say that the integral between 4 and 2, we write our upper limit up here and our lower limit down here. So we can say of root x with respect to delta x. This can be modeled both as sorry, I lost my words there. Essentially, as the strips get infinitesimally smaller and smaller, the area to approximate becomes almost perfect, essentially. So it gives an exact answer. So what we do is that we rewrite again as x to the power of a half delta x. And then what we do is we consider square brackets. So in the square bracket, we integrate this term. So this term becomes x to the power of 3 over 2, because a half plus 1 is equal to 3 over 2, divided by 3 over 2. Now, we put our upper limit on the top right-hand corner and our lower limit on the bottom right-hand corner. Obviously, when something is divided by 3 over 2, we will get 2/3 x to the power of 3 over 2 between the limits 4 and 2. Now, what we do is that now we can calculate 2/3. Sorry, we substitute our limits in now. Now, what it is it is your upper limit minus your lower limit. So let me show you. So 2/3 times 4 to the power of 3 over 2 minus 2/3 2 to the power of 3 over 2. And then I don't have a calculator on me at the moment, so and then you'll get your answer out of it. And hopefully that will work out. Now, just a little note that it's upper limit minus your lower limit. That's meant to be a minus, not a divide sign. I hope that's completely understanding, and I hope that is completely reasonable, and you hope you understand. Okay, let's move on to something that I want to just discuss and make sure, and just to clarify, essentially. So let's consider the definite integral of 7 into 6x to the power of 5 minus 3 root x. 3x to the power of 5 over 2. Let's do that. Sorry about that. So there are two ways of going about this. You can just simply integrate it like this, or you can factor and separate the integrals. So what I mean, I'll show you that way. Oh, focus. So what this is saying, what I'm saying is that you can say that 6, you factor the 6 outside on this side, between 7 and 2, x to the power of 5, with respect to dx, minus 3 on the outside, because it's a constant, we no longer need it, between 7 and 2, x to the power of 5 over 2 with respect to dx. I find this way much more easier because you always know what you're doing and you know where to put your where to apply your technique. So, integrating this, in the square brackets we go. So we have x to the power of 6 over 6 between 7 and 2 minus 3 x to the 7 over 2, and then that's 2/7 because obviously we're dividing by 7 over 2, which becomes 2/7 between 7 and 2. So what we do now is 6, applying our limits now, so it becomes 7 to the power of 6 divided by 6 divided by 2, minus 2 to the power of 6 over 6 minus 3 2/7 7 to the power of 7 over 2. Minus 2/7 2 to the power of 2 over 7. And then obviously you'll get your answer out of it. Now, it is best to keep in mind that either you give it in 3 significant figures, but more ideally, an exact value. So what I mean by an exact value, for example, if you have a pi, for example, in your equation, it's best to give it either in terms of pi or rational numbers. That's how you write as a rational number. And then that's pretty much laying the foundations down on integration. I hope you've... Oh, sorry, I need to give exercises out, don't I? Okay, so I'm just going to start off really simple. So, just going to say find. Okay, so those are your definite integral exercises. I hope you've enjoyed. Please give a video a like and please subscribe as well for more quality videos. Well, not really quality, but helpful videos like these. If it didn't help, please go to a friend, a teacher, or whoever is available to be able to help you on these questions. I hope you enjoyed. Thank you for watching, and I'll see you guys later.